All right, we're ready to start talking about the oceanography section of this class, and we're going to start with the ocean floor. Now, we've already had a little bit of information about the seafloor when we talked about seafloor spreading in World War I and World War II, leading to the discovery that the seafloor was actually quite varied. All right, you guys, so here's some background information. If you look at a globe or a map of the Earth, what is really surprising is how little continent there is and how many oceans there are, how much oceans cover the surface of the Earth. So 29% continent, 71% ocean. Now this makes us unique in the solar system. Remember that when we go out and search for signs of life, we always look for water. You're going to find out what a miracle water is, and we really do believe you have to have water to have life. We're the only planet or moon that has a liquid water ocean. All right, if you again see a map of the Earth, and what you're going to notice is that the oceans are all interconnected, and this does matter. So we do care if somebody in a faraway ocean is dumping trash or nuclear waste or something in it, because they're all connected, and eventually it will interact with our ocean basin. All right, liquid H2O, obviously, if we talk about the hydrosphere, most of the liquid water on Earth is contained in the ocean, and if we just kind of consider H2O as solid, liquid, or gas, it's still, the oceans make up a huge percentage of all the H2O found on Earth. All right, the ocean is amazingly important. I was an oceanographer, so I can't get this point across. It is what makes our Earth's climate stable. So what I need to do with this lecture and the next couple of lectures is kind of to give you guys some of the basic relationships that have been going on for very long, but then I also have to tell you about stuff that's happening recently because of human practices, because of global warming and global climate change. And it's kind of sad because the ocean is our best friend. It's been doing us a big favor for a very long time, and we are really messing with it. The ocean has done as much as it can, and now the changes are going to be happening more quickly. And if we don't do something about this, we may be very sorry. Now, I'm very hopeful, so take this as let's do something about it. Let's not just lie down and die or anything. All right, now again, I'll show you guys some slides here. The northern hemisphere, if you can see a map of the Earth, check it out. Most of our land masses are concentrated in the northern hemisphere, with much fewer land masses in the southern hemisphere. And this does change some of our patterns, oceanic circulation patterns, wind patterns, etc. So they're not exactly symmetrical because the distribution of continent in our hemispheres is not completely symmetrical. All right, now at the top you've got a view down from Santa's workshop, or the North Pole, and what you see is a lot of land masses. You can see North America, Eurasia, etc. And so if you look from the South Pole, you see the Antarctic, and remember, underneath that ice there is continent. See a little bit of Australia, South America, and Africa. But one thing you should notice is the ocean completely circles Antarctica, and in fact that's the only place on Earth that we have a current that goes completely around the Earth. And in fact, that's why there's so much ice at Antarctica. It's because we basically cut off the heat flow from the lower latitudes, from the tropics and the equator to that polar region. All right, let's learn a little bit about our oceans. Look at the Pacific Ocean. That's kind of what I consider our ocean. It's the largest ocean. It's both in the northern and southern hemisphere, so it's really big. It's also the deepest ocean. It's the oldest ocean basin. It's just amazing. The oldest seafloor that's in place is in the Pacific Ocean. All right, the Atlantic Ocean is a little bit smaller. It's pretty young. It opened up when North America, Europe, Africa, and South America pulled apart after the formation of Pangaea. It is both in the northern and the southern hemisphere, and it's growing. It's not quite as deep as the Pacific Ocean, but it still has some pretty good depths. All right, the Indian Ocean. Now, the Indian Ocean, kind of surprisingly, is almost as big as the Atlantic, but look at it. It's mostly in the southern hemisphere. There's very little of it in the northern hemisphere, and that little portion in the northern hemisphere is pretty wild. That's where you get those monsoons, the monsoons that are really famous in India and Southeast Asia, and I'll probably talk to you just a little bit about that at the end, just because, if you don't like rain, don't go to Southeast Asia in June or July, because you might get hundreds of inches of rain, and that's normal. All right, now kind of interesting, you guys. Look at the southernmost part of the Pacific Ocean, the Atlantic Ocean, and the Indian Ocean. That has been kind of at 50 degrees south latitude and a bit larger than that. That's called the Southern Ocean, and that's because it behaves very, very differently from the rest of the Pacific, Atlantic, and Indian Oceans. And that has to do with that current that goes all the way around the Earth. So it's called the Southern or Antarctic Ocean. And we're going to talk a little bit more about it. The smallest ocean of all is the Arctic Ocean. It's small, it's shallow, there's ice up there, the Arctic ice cap, but remember, no continent under that. It's just ice. All right, so largest and deepest for Pacific, we talked about that. Yep, we talked about that, we talked about that. So, someday I maybe have to change this slide because they're thinking in your lifetime there may not be any more permanent sea ice in the Arctic Ocean. That makes me sad. All right, and then that Southern Ocean or Antarctic Ocean. It's at 50 degrees south and farther south, 50, 60, 70, etc. degrees south, and it includes the southernmost portion of the Pacific, Atlantic, and Indian Oceans. All right, now most of you guys are probably familiar with topographic maps. And topographic map, zero sea level, and for instance, the Mount Whitney quadrangle, the Mount Whitney map, it's got some number on it, I think 14,000, I don't know what it is, 282. Okay, and the 14,282 would represent feet above sea level. Okay, but on a bathymetric map, 0 is sea level, but the 14,282 would represent feet below sea level. So the bigger the number on a bathymetric map, the deeper it is. On a topographic map, the bigger the number, the higher the elevation. Now, I'm not going to test you on that. It's not really that important, but it's just kind of being proper because we are going to be talking about some very great depths. All right, we talked a little bit before about how during World War I and World War II we really had to find out as much as we could about the ocean basins, and this led to realizing the ocean basins are quite complex, that they have these underwater volcanic mountain ranges called mid-ocean ridges, and this led to seafloor spreading and ultimately plate tectonics. Now, echo sounding, I think you mostly are probably pretty familiar with echo sounding, and it was invented in the 1920s, and it was our primary instrument for measuring depth, and we still use it. It's a training tool, and you're in a ship and you send off kind of a little sound wave, and we know how fast sound travels in water, and then the sound wave bounces off the bottom, so you know the depth, and then it comes back up to the ship. Now I'll show you guys the slide. The trick is to remember to divide it by 2, because when it comes back up to the ship, it has gone through the ocean water column twice. It goes from the ship down to the seafloor, and then from the seafloor up to the ship. So that's why it's kind of used as a training tool for first-year oceanographers, and I made sure I divided by 2 so I didn't get in trouble. All right, here it is. You send off the little kind of sound wave explosion type thing. It sends it down, it bounces off the floor, and this is not too different from the idea of a fish finder. So obviously a large school of fish could interrupt that signal and give you a little bit of a false reading. So if you're an oceanography student and you forget to divide by 2, you may run aground that ship and you would be in very big trouble. All right, now much more high-tech data. This is what we oceanographers use. We pull something behind called a side scanning sonar. Now, guys, kind of on a sad note, if you remember that little 2-year-old boy who was kidnapped by the mother's ex-boyfriend, and they found them later dead in a canal down by, I don't know, Patterson or something on Highway 5. I was kind of surprised that they're using that piece of instrument to look in that murky water in the big canals to find lots and lots of different cars and things like that, but also, and ultimately ended up being kind of a sad story. But what happens, he goes on these oceanographic tours, and it's kind of like mowing the lawn. If you mow the lawn systematically, you go up one row, you take a sharp turn, and you go down the next row so that you cover all the ground. And this is very high definition data, and you can kind of see that picture on the bottom is from one of these cruises, and I purposely left out one of the slices of information because we haven't finished mowing the lawn, but it gives you very, very detailed information. Now, if you're sailing your boat around the world, you don't need this much detail, but if you're driving Alvin or a Navy submarine or on a research cruise, you need this much detail. If you're working on a PhD on mid-ocean ridges and things like that, you need this detail. It's very time consuming. As an undergraduate at both UC San Diego and UC Santa Barbara, if you're a good student, you could probably go on one of these research cruises and you're at sea for like 30 days and it's a great experience. It's just harder to do when you have family, animals, house, mortgage, etc. All right, now obviously a lot of our lower resolution data comes from satellites. And those satellites are up there, practically 24/7 taking all this data. And it's kind of funny, they're not measuring the elevation of the sea floor by bouncing radar waves off the sea floor. The ocean's too deep for that. They actually look at sea surface elevation, and it's kind of crazy, you guys. I'm pretty into sea surface elevation. It tells you a lot of stuff that's happening on Earth. In fact, if I can just look at sea surface elevation, I can tell you if we're in El Nino or La Nina. But in this case, the topography or the bathymetry, the shape of the sea floor is mimicked by the shape of the sea surface elevation. So tons and tons of data. This is the type of data that you would use like in a typical oceanography class or to have your sailing charts or things like that. So look at this. This is how that sea surface elevation mimics the sea floor bathymetry. So when things stick up, the water mounds around it because of gravity, gravitational attraction. So it's not super high resolution. If you're dragging, Gloria, that side scanning sonar, and you're using low resolution elevation, you might lose Gloria. And I have a friend that did that. And he's no longer an oceanographer. That's not a good thing to do. It was his choice, but it was probably been a rough life for him to be an oceanographer after being one of the people that lost Gloria. All right, and this is that low resolution data, but you know what? It's good enough to show us where the mid-ocean ridges are in Hawaii. You can see the Hawaiian island chain, the hotspot, and a lot of other cool features. All right, now what we're going to do is we're going to look at the three major regions of the ocean floor. Remember, it's not like a bathtub because it would be the world's most uncomfortable bathtub due to the third region. Now, the continental margin is the region closest to the continent. And you have two choices. You can have a passive continental margin or an active continental margin. The west coast of the United States is active. We have a plate boundary here. We have the San Andreas Fault, which separates the North American plate from the Pacific plate. But the east coast of the United States is a passive boundary. Remember that our plate includes the North American continent, much of it, and part of the North Atlantic Ocean. And so the east coast of the United States, the sea floor and the continent are glued together. There's no arrow action, no arrows coming together, pulling apart, or sliding by each other. And we call that passive. All right, then you go off the continental margin, and we'll talk about the different parts here in a second, and you go to what's called the ocean basin floor. Now, this is kind of the bathtub model. This is the deep part of the bathtub. It's deep water, it's farther from land, and talk a little bit more about what you find there. All right, and then you're walking out along this bathtub, deep ocean floor, and all of a sudden you're climbing up a hill, and it turns out to be an underwater volcanic mountain chain known as the mid-ocean ridge. And it's shallower. You may be at 20,000 feet at the ocean basin floor, but when you climb to the top of the mid-ocean ridge, you may only be 6,000 feet below the sea surface. So they really do kind of stick up pretty high, and they make up a major portion of the sea floor. All right, so here's a cross-section through North America to Africa through the Atlantic Ocean. And if you look on the left-hand side on the bottom, you start on the North American continental margin, and you go out into the deep ocean basin floor, and that's kind of the bathtub model. Now look in the middle. That's what ruins the bathtub model, that mid-ocean ridge. So about where that line is that separates the mid-ocean ridge from the ocean basin floor is where you start climbing uphill. Okay, you climb uphill, you climb over the mid-ocean ridge, you climb back down, and you get to the other side where you're in the ocean basin floor. And then you can actually keep going and climb out onto the continent of Africa. So that's kind of what it looks like, running right down the middle of the Atlantic Ocean. All right, what we're going to do is we're going to look more closely at the continental margin and at the different parts of it. And we're going to actually start with the passive margin, so what we would find on the east coast of the United States. Now, remember also that the Atlantic Ocean only opened fairly recently. And because of that, it's completely surrounded by passive boundaries or passive margins. So off the east coast of South America, we've got a passive boundary. Off the west coast of Africa, we've got a passive boundary. And off the west coast of Europe, we have a passive boundary. The Pacific Ocean is much, much older, so the plate motions are much, much more varied. And over time, the Atlantic Ocean will become more complex. But it's just a perfect model right now because it is such a young ocean. It's like 135 to 150 million years old. Now, the east coast of the United States really doesn't have to worry about volcanoes. There's no volcanoes. Very few earthquakes, not like what we have to worry about. And, it's just kind of what I would call tectonically not super exciting. It's also low-lying, and we'll talk more about that. All right, when you go start walking off into the water and your ankle height, of water, you are on the continental shelf. And it's called a shelf because it's pretty flat. It has just the slightest grade. And what it is it's part of the continent that is periodically exposed or flooded by water depending on sea level. Now the continental shelf, if we went ahead and took those cores that we do on the Ocean Drilling Project ships, at the bottom of all those sediments we would keep finding granite. We would not find basalt, we would find granite because it is part of the continent. Now this is kind of interesting, you guys. You might say, well, I'm not going to be an oceanographer. Well, that's fine. But if you become a lawyer, you care about this because there's the law of the ocean. Each country owns its continental shelf. We own the continental shelf off the United States. And on our East Coast, we actually own more of the ocean. Not only do you own all the rights to the minerals and mining and stuff on the sea floor of the continental shelf, but you also own all the rights to the fishing and anything else like that. It's in the water column above it. And believe me, we protect this like you wouldn't believe. And so we actually own more of the ocean and sea floor off the east coast of the United States because on a passive boundary, the continental shelf is wider. On the west coast, because we have an active boundary, our continental shelf is much more narrow. All right, and it does. I mean, the continental shelf, that's where most our oil reserves are and our phosphate reserves. And believe me, I like seafood. All our seafood comes off of continental shelf. All right, especially on the East Coast, much of our continental shelf is really covered by glacial deposits from that last ice age. Remember, North America had a huge, maybe a mile of ice on that continental ice sheet over it, just 12 to 15,000 years ago. So if you've ever been to Long Island, Martha's Vineyard, and even parts of Manhattan, a lot of those are actually glacial deposits. All right, so lots of thick sediments that are coming off the continent because remember, whatever sticks up is being eroded and it usually ends up down at the ocean and it ends up on the continental shelf for the time being. Obviously, if you get too much on the continental shelf, something's going to happen. Now, sea level changes periodically, and right now we're in a time of rising sea level, but at the height of the last ice age, so much water was tied up on the continents that they think that it was about 120 meters lower sea level. And so, if you wanted to study Native American tribes that lived on the east coast of the United States 12,000 years ago, you'd better be a good scuba diver because that stuff is underwater. All right, so again, that's our property, and believe me, that's why we have a Coast Guard and Merchant Marine, and we go after anybody messing with our property. All right, so here it is. So you can see the continental shelf. Well, first of all, you guys, this has a vertical exaggeration. If it did not, it would look pretty flat to you. And let me just explain this. Think about the tallest place on Earth, or what sticks up highest above sea level, and that's Mount Everest. And that's something like 5 to 6 miles above sea level. Well, if the highest point above sea level it sticks up is 5 to 6 miles, but if I had to buy a belt for the Earth, that belt would be 24,000 miles long. Even Mount Everest, if we don't do a vertical exaggeration, it doesn't even register. Because think about it, you got $5 or $6 in one pocket, and in your other pocket you got 24,000. Boy, I know which pocket I'd rather have. There's a big difference. And so we do this, you can see the VE, it's a 10 times vertical exaggeration. It just makes your life easier. All right, so you can see the pretty flat continental shelf. It's even flatter than that. And then we're going to talk about what happens when you can see the slope angle changes. And then we're going to go into the next region known as the continental slope. All right, the continental slope. Somewhere underneath the continental slope, if we're taking cores, we will go from granite at the bottom of our core to basalt. Okay, so this is going to be the seaward edge of our continental material. It's relatively steep. It's definitely a lot more steep than the continental shelf. All right, now we've got to talk about submarine canyons, and I think most of you are familiar with the Monterey Bay Aquarium. It is ideally situated. It is right on the mouth of the Monterey Bay Submarine Canyon, and that just makes it so much more interesting. There are literally these submarine canyons that are super deep, and they come right up and sometimes to the shore. And if you're a scuba diver, you have to be a little careful because you can get in trouble by going deep. You know, it's not good. You don't want the bends. You can die. So you always have to be really careful about how deep you are. You don't want to get too deep. And they're very steep-sided, they're cut very deep, and they go down into the deep ocean pretty quickly. Now, most of them are eroded by underwater landslides called turbidity currents. Now, when you guys did your rock walk, remember we actually looked at a chunk of one of these rocks because a lot of them have been exposed on the surface of the Earth due to uplift, especially on the west coast. And so you've seen these turbidity currents or turbidites. And sometimes you have seaward extensions of river valleys. That used to be kind of the main hypothesis, but that's been rejected because I can tell you if we used to have a river somewhere by the round deposits, rounded rocks, and a lot of these we don't have any river deposits upstream from them. So that was kind of, you know, some of them it does, but a lot of them it doesn't. And again, Monterey Bay Aquarium is your great example. Okay, here is a diagram of a submarine canyon. You can see the continental shelf, and remember, stuff is piling up like crazy on the continental shelf because of erosion, and it becomes unstable. And you know, anything from a severe storm, a hurricane, an earthquake, to just getting too much stuff, and it's going to move down slope. And boy, if it gets that continental slope, it's going to, you know, move really fast. And it's kind of like if you ever fill off your bike on gravel, you get all ground up. You know, when this stuff moves over the sea floor, it grinds it up, and so you end up with this very steep-sided canyon. Now at the bottom you can see the stuff comes out and deposits, and that abyssal fan is what would be my turbidity currents. All right, so turbidity currents are basically underwater mass wasting events, underwater landslides. They are obviously saturated with water, and it's like being hit by a freight train, not like being hit by a little wall of water. Gravity is the driving force of all mass wasting. That's what keeps them in motion. And so we're going to talk about in passive margins, we're going to create a pile of sediments that we're going to call the continental rise. And those pile of sediments that are kind of that apron at the base of the continental slope are created by these turbidity currents. All right, I'm going to show you guys a picture of a turbidite that I took at Salt Point, and it's I'm not a very good photographer, and if I go back I'll take better pictures, but every time I've ever been out there I have run into professional photographers taking pictures for geology textbooks. And so because our west coast of the United States is emergent, it's rising up, and we'll talk more about that, it's a great place to see these. So here it is. Now another place to see this would also be if you go to the Point Reyes Lighthouse. You know, when you stand at the top of those stairs and say, do I really want to go 330 stairs down and then have to come back up? That big outcropping of rock right on the right hand side is a turbidity current deposit. Now, it's kind of hard. I'm going to probably have to try to mark this picture up in some way for you. This is a series of different landslides and underwater landslides. And what happens is you can see, if you kind of go to the bottom, let's just see if I can't talk you through this. Go to the bottom and you can see that kind of dark area, and then you see kind of a straight line. Start from there. That's the top of an old flow and the bottom of a new flow. Now rise up and you can see it's big and chunky and gravelly, and then all of a sudden it looks kind of like sandstone. Okay, what's happening is this is called graded bedding. The big stuff gets deposited first, and then as you move up, you get smaller and smaller. So we're going from like cobble and boulder to gravel to sand, and finally at the top, you're up in the silt and clay. Now then you can kind of see kind of a straight surface. That was the top of the mass wasting event. Then sometime later, another mass wasting event happened and sat on top of that. And then you can see a little bit cut off in the upper left-hand portion. You can see a little bit of the top of that next one. So we actually have 3 different mass wasting events visible in here because we have 3 sets of graded beds. All right, now on the right bottom, you can see the pictures of the graded beds. And so the landslide starts with the coarsest stuff, and then it gets finer upwards. And then the next pulse of landslide, coarsest stuff, fining upwards. So these underwater landslides, and the way we learned about these is they used to take out our transatlantic cables. You guys, we didn't always talk to grandma in Europe through satellite links. We used to actually have to talk, and the phone lines went across the Atlantic Ocean. And, when I was growing up, we were in the Cold War. We were sure that, the Russians were going to nuke us and we were going to nuke them and it would be horrible. And so, the President of the United States carries around this little football thing that has like launch codes for our nuclear arsenal, and it's just horrible. But what happens, we were at a very high code, and in fact almost maybe caused World War III, when a turbidity current went and knocked out all these phone lines. Remember, a lot of our allies are in Europe, and we'd want to talk to them and stuff before we started launching things. And when they started getting all knocked off, they thought, oh, some Russian subs down there cutting these lines so that we won't communicate and they can just nuke us. And luckily, they were going in a very consistent manner at much too fast a speed for a nuclear sub to do. And some scientists, said, no, this is nature. And so they got a submarine down there, and they could actually see the landslide deposit. So, phew, disaster narrowly averted. All right, now the continental rise, that pile of sediments, is only found in a passive margin, and there's a reason for that. In an active margin, we have a trench and an accretionary wedge, and that's where they go. They don't go to this nice little apron of passive sediments sitting there. And so what they do, it's kind of cool. I'll give you guys an analogy when I get to the picture, is they soften the slope where the slope meets the ocean basin floor. And I'll give you my analogy of a black diamond run and maybe not quite a bunny run. What's the one? The green run? I don't know. That's green's blue run, intermediate run. And that thick pile of sediments does soften the slope. And that thick pile of sediments is kind of cool. All right. So let me kind of see, what I'm trying to do is, for the people that don't get to see this, I'm putting in special slides just for you of things that I would normally say. So what I'm going to do is move over here and say them. All right, right here, I like this shot because this is a passive margin, and you guys can see that. Remember, why do you get a passive margin? Because of continental rifting. Continental rifting takes continents, thins them, stretches them, and creates new sea floor. And so you can see that that part of the continent that's periodically flooded is the thinner part of the continent. And you can see it glued to the oceanic crust. So imagine you're in that ship taking cores, and you go across the continental rise and the continental slope. At some point, you're going to go from finding basalt at the bottom of your core to, as you move inland, you're going to start finding granite at the bottom of your core. You can also see the very flat continental shelf. You can see the much deeper continental slope, and you can see the sediments making their way down through a few of those submarine canyons and making piles of sediments along the continental slope deep ocean floor boundary. All right, here's my analogy of the Black Diamond Run. See the kind of brownish, tannish sediment pile? Take that off. That kind of looks like a Black Diamond Run to me. But by letting those sediments pile up, the slope is much less steep than it was before, and it becomes kind of an intermediate run. If you're ski talk, okay? I'm from Santa Barbara. We don't do ski talk, but there's my ski talk. And what you can see there, the continental shelf, the continental slope, and the continental rise are all parts of the continental margin. Once you move past that, you are in that second province, or the ocean basin floor. Now, if you look at the bottom picture, there's a little bit less vertical exaggeration on that. Still has some vertical exaggeration. You can see that, and it looks a lot flatter. You'd have a hard time pointing out the different parts, but if I put lots of vertical exaggeration on it, you can easily point out the different parts. All right, so we've been talking about a passive margin and where we have the passive margin on the left. Now we're ready to talk about an active margin, like what we're showing on the right. We have a shelf, it's just going to be shorter. We have a slope, it's going to be steeper. It's not going to the ocean basin floor, it's going into a trench. And remember, the deepest parts of the ocean, Mariana's Trench, is 36,000 feet deep. And then we'll get out to the ocean basin floor. All right, so in the active margins, you basically have a trench, and remember the trench is where an oceanic plate is being subducted either beneath a continental plate or another oceanic plate. The Pacific Ring of Fire, that's where it's happening, you guys. It's all active. You're going to have the sediment that comes off the continent not pile up. In fact, it'll either end up in that accretionary wedge, what I call the cowcatcher, or it will end up down the trench, being melted with the flux melting and ending up creating those nice gray volcanoes. All right, so the differences. Passive margins, boring. No, it's not. That's not very nice. But tectonically, they are boring. No earthquakes, no volcanoes, and no mountain building. Okay, you do have a wider continental shelf, so you got more property for seafood and for mining and drilling and stuff. The slope is more gentle because it's not going into a deep trench; it's going to the ocean basin floor, and you do have a continental rise. You are able to pile up those sediments. All right, in an active boundary, you're going to have earthquakes because at all plate boundaries you have earthquakes. You're going to have volcanoes, and you're going to have orogenesis, which means mountain building. All right, it's more narrow. We own less property. It's steeper. It's going right into the slope is steeper. It's going into the trench, and you do not have a pile of sediments known as the continental rise. Those only form in passive margins. All right, we're now out into the ocean basin floor. Any cores you're taking on here, you're going to end up with basalt at the bottom of them. We're beyond the continental margin, deeper in the ocean. Okay, and this will include in an active boundary the deep ocean trenches, but in a passive boundary it will include the abyssal plain. All right, you already know a little bit about deep ocean trenches. Remember, that's where seafloor is being bent back under, shoved into the asthenosphere, and melted. And so they're long and they're narrow. Go find a map that has these on them, and off the coast of Chile and Peru, you can find the Chile-Peru trench. Off of Central America, you can find a trench. Off of the Aleutians, you can find a trench. Off of, all of the western Pacific, you can find lots of trenches. And in fact, find the Marianas Trench. That's a pretty impressive one. And remember, right parallel to the trench, we are going to find a line of gray volcanoes, either on the continent, like in South America, or on the sea floor, like Indonesia or Japan. All right, and here's that shot right from plate tectonics. Oceanic plate being shoved under something that's less dense, in this case a continental plate. The trench, parallel to the trench, we have the line of gray volcanoes. We've got the line of flux melting coming up, which is a lot of those sediments and water mixing with a little bit of the asthenosphere and melting and rising up because it's less dense. All right, you guys, we're off to the abyssal plains, and look at the name. Abyss means deep, plains means flat, and these places are very deep and they're very flat. It's kind of interesting. Engineers like to make flat things sometimes, and I don't even think they could engineer a place as flat as this. Now, the reason it's so level is because of something called suspension settling. Sediments lay down horizontally. It's just the way. It's physics. So they are really, really flat. All right, so like we said, suspension settling of those very fine-grained particles, and most of that is either coming out in the ocean currents or even being blown out very far distances by wind. Wind can carry clays hundreds of miles, probably actually thousands of miles out over the ocean. Now, that's a pretty slow rate of accumulation. This is pretty far from land. You only get your abyssal plains very far from land. So 1 millimeter, you guys think about a millimeter, it's tiny per 1,000 years, but there's a whole lot of 1,000 years in 100 million, so they get very, very thick. They take a long time to build up, but they can be very thick in our oldest of our sea floor. All right, and we do mainly find them off passive continental margins, but because the Pacific is so darn large, we actually have some places that are so far from continents and islands that we have abyssal plains. And in fact, some of the most famous abyssal plains are the ones that yield manganese nodules in the Pacific. All right, this is really cool. This is called seismic reflection profiling. And so we actually use like kind of small controlled explosions, and it's kind of like a sonogram. And looking through, the mother's stomach or the mother's womb at the baby, you pass it through, and the different parts, and the different rocks of different densities and sediments reflect back the seismic waves in different ways. And so what you end up with is a beautiful picture of what's going on. You can actually see the basalt, and remember, once you move off the mid-ocean ridge, you start accumulating sediments. And so usually the basalt is completely covered, but in this case they have one abyssal hill sticking up. All right, we are at the mid-ocean ridge, the thing that kind of, ruins the bathtub picture, but that's okay with me. I like the mid-ocean ridges. Now, mid-ocean ridges are a very significant feature on our Earth, and in fact, continents cover 29% of the Earth's surface. The mid-ocean ridge system covers about 23% of the Earth's surface. So this is that underwater volcanic mountain range. It runs right down the center of the Atlantic and down the east side of the Pacific, also runs in the Indian Ocean. If you find a tectonic map, you can pretty much follow it right along and around the Earth like the seams of a baseball. So that's where new seafloor is made, right from our last section. We've got lots of basalt coming out of there. The Earth pulls apart, the two plates pull apart, and up comes the blood and serum of the Earth, or basalt, to fill it in. All right, so we're going to talk about some of our different types of sediments. The seafloor is covered by sediment. Remember that you'd be like, well, where's the basalt? The basalt is underneath all those sediments. Different sources. We can have stuff brought out by wind. We can have things brought out by currents, but a lot of sediments come off the continents in those turbidity currents. So it's those mass wasting events. And they do, the material does slowly settle down and covers over the seafloor. In fact, a lot of it's actually biological, and we'll talk about that. Obviously, the thickest sediments are closest to the continents, and the thickest of all are in the trenches, where you not only have material coming off the continents or the islands, but also coming in on the seafloor plate that's subducting. All right, there are four main types of sediment: terrigenous or lithogenous, and this is coming from land. And this is the most common, so I've got them in order of their sheer volume. The second most is biogenous, biology, created by life. Yeah, whole sediments are made up of little skeletal pieces of organisms. Hydrogenous. Now, you guys, we talked about chemical sedimentary rocks. It's basically the same thing. These form from water. That's the hydro part. And these are those ions that are suspended in water. And when the ions are able to come together for various different reasons, we will form sediments. And obviously, table salt, sea salt is one of them. All right, the last and least significant amount, but still quite a large amount, is stuff that rains down from space. And until recently, it was obviously all natural. Now we have man-made junk starting to rain down from space. But cosmos, space, so coming from space. All right, terrigenous or lithogenous, obviously the continents really do produce quite a bit. Anything that sticks up is going to be eroded like crazy, and so those sediments end up on the continental shelf and end up down in the ocean. So coming from islands and continents, almost every part of the ocean receives some of this. The finest grained stuff can really travel far. This material tends to be oxidized, so rusted, a lot of red colors and brown colors, and that helps you to know that it's been well oxygenated and it's been in contact with the Earth's atmosphere and the surface. All right, this is a great slide. The Sahara Desert, it runs along, what would that be, northwestern Africa. And it has sustained winds in certain directions. And you guys, this is going out into kind of the South Atlantic Ocean. And this is not rare. The last slide in this series will actually show you this, that this wind belt has been moving in this direction for a long time. And this is not sand, you guys. This is silt and clay. Sand is left behind. It's too large. But the wind can really carry that silt and clay. And in fact, if this wind was strong enough, it could create a smog day, because smog is not all man-made. It's particulate matter that you don't want to breathe. It could actually create a smog day across the ocean. So kind of crazy. All right, biogenous. Now, little organisms that live in the ocean make their little skeletons out of different material, including silica and calcium carbonate or calcite. Now, you see the word ooze. When you take cores, they actually are like oozes. They're like the gel in your shoes and running shoes. Until they are finally, lithified. So when you go down, then you'll actually get into rocky material. But before they're fully lithified, they are like gel material. And sometimes that gel material would fizz with acid. It's calcareous, and sometimes it's silicious. Or, the material could actually scratch glass. In warm water, you tend to get calcareous. sediments. And in cold water, like we have off our Pacific coast, you tend to get organisms that make their shells out of silica. There's a reason for this. Think about a very cold soda. It tends to be very bubbly. But let's say you have a soda and it's warm. Even if you don't have the lid off, then you take the lid off, it's kind of flat. Cold water can actually dissolve more CO2 in it. And so if you dropped an organism that makes its shell out of calcite in very cold water, it will dissolve the shell. So those organisms don't do too well in cold water, obviously. They need their shells. So warm water organisms are dominated by ones that make their shells out of calcareous material, calcite. And then in cold water, we're really dominated by the diatoms and the radiolarians, the things that make their shells out of silica. All right, this is really cool, you guys. Everybody's had chalk in their hands. This is the little organism called a coccolithophore, or a coccolith for short, that is actually photosynthetic. It has its little shells out of calcium carbonate, and it lives up in the sunny parts of the ocean, obviously, if it has to photosynthesize. And these make huge deposits of chalk. And what you can see is those little shield-like things, and maybe 20 or so of them. And when the organism dies, it falls to the seafloor. The little center part of it, the organic part, rots, but then those little shields are buried, compacted, and lithified, and it creates chalk. All right. One of my students one time asked me if we man-make chalk by chemical means, or if we mine chalk to use. And I said, well, we can find out. And I grabbed a piece of white chalk right off the board and took it in to the biology department and made a slide, and this is what we looked at. And if you can see, look for those little ring structures. The chalk on the white chalk right in the front of the classroom was actually mined in its organisms. You can see the little shield type things. Okay, here's another shot. So you can see there's definitely biological material in this. All right, talking about chalk, I think a lot of you guys have probably heard of the White Cliffs of Dover. Some of the cliffs in England are pure chalk. These are the cliffs that make up the English side of the English Channel, and on the other side is France. And they are more than 300 feet high. So here's a picture, you guys. There's a huge barge in front, and then in the far distance you can see a little lighthouse up on the right on the top. Those huge white chalk cliffs. Now, got a little quick calculation for you. You guys, I use a lot of simple math. This is what I call the happy homeowners math. And so if a typical biogenous ooze, such as calcareous ooze, accumulates at 1 centimeter per 1,000 years, how long did it take to make the 100-meter tall White Cliffs of Dover? So I'll give you a second. Why don't you go ahead and pause this and try and figure it out. And the next slide will actually show you. So pause this, please. Try and figure it out, you guys, because, this is reality. All right, so if you look here, 1 centimeter is equal to 1/100th of a meter. And so I do what I call a ratio and proportion. These are so useful. I use these all the time. If I want to make Toll House chocolate chip cookies, it calls for 3.5 cups of flour. What happens if I only have 2 cups of flour? I can just use ratio proportions, make a smaller batch. So if it takes 1,000 years to lay down 1/100th of a meter, how many years, X, does it take to lay down 100? And so if you remember that cross multiply the 100 by the 1,000, and then divide by the 0.01. And what you get is 10 million years. It took at least 10 million years to lay down those cliffs. Wow. All right, now this is my specialty, little organisms that make their shells out of silica, because this is what lives in the Pacific Ocean. Look on the left, that's one of the forms of a diatom. Diatoms are little organisms that photosynthesize, and they give us most of our oxygen. They also are the organism that produces, petroleum. Everything that you see, if you see oil wells off the coast, that's what they're mining. They're getting that, and that organism has a little drop of oil in it. It's photosynthetic. It has to be up. Where photosynthesis is happening in the surface waters. So when it dies, its little carcass falls to the seafloor, and the outer part, which is made up of silica, becomes diatomaceous earth, or the rock diatomite, but the little drop of oil is changed over time into petroleum, gas, oil, etc. All right, in the center you've got a radiolarian. This makes radiolarian chert, which is pretty well known in Northern California. And it's called a radiolarian. Look at those radial spines. They all look like torture devices. And on the right-hand side, what you have is a siliceous ooze. Really, lots and lots of organisms. And I pulled up cores where this is exactly what the surface looks like. Now, the Monterey Shale is actually a biogenous sediment, and it goes all the way from Point Arenas to Baja California, along the coast of California. And it's got a lot of diatomaceous material in it. All right, the third type are hydrogenous, kind of the equivalent to chemical sedimentary rocks. They crystallize directly from seawater. Temperature changes, evaporation of water, chemical reactions, things like that can cause things like manganese nodules, calcium carbonates, limestone type stuff. The metal sulfides that we saw at the mid-ocean ridges, and then things like sea salt evaporites to form. Now, you guys, I put a little short video, a link to it to YouTube, about these manganese nodules. These are really, really important, so please do watch that. It's just really short and it's kind of cool. And these are, potentially very important to us because they contain a lot of rare metals that we need, and they're in short supply. Now, obviously, it's not super easy. They're very deep. And this is not a renewable resource. This is a one-shot deal. It takes so many, tens of millions of years to form these that once we pick these things up, there's not any more left. All right, the last type, which is the least significant, but still hundreds of thousands of tons of this material falls onto Earth, is space-derived material. Think about all the shooting stars, not to call them that, meteorites that you guys have seen coming through our atmosphere, and the dust of that material ends up in the ocean floor. And so it's pretty cool when you're looking at your cores, you find these things all the time. I've found a lot of little ones. I've never found a big one, but I've talked to people that have found big ones. And typically the really little stuff is perfectly round because as that material goes through our atmosphere, it melts and it's kind of very fine, and then it cools rapidly, and it's just that aerodynamic shape that it gets. So again, the composition varies, but it's very, very interesting. All right, here's that last slide. Now, you guys remember that Saharan sandstone? Look in the Atlantic Ocean, and you can see that little area of the fine abyssal clays. That's the material that's coming off, and you can see it up by northern America too. Look where the yellow is. That's kind of the most interesting to me. Yellow tells you have cold water. And you might look and say, oh my gosh, in the equator in the Pacific, why is there cold water? We'll talk about that. It's called upwelling. And there's two reasons we have cold water off the west coast of North America and South America. We have upwelling, but we also have a cold surface current, and we'll talk more about that too. And typically in areas where you have upwelling in the yellow, you're going to have good fishing, because if the base of the food chain is happy, everybody up the food chain is happy, including sushi eaters. Now look at the kind of light purple, that's relatively warm water, so obviously the life form that dominates are the calcareous life forms. And then obviously surrounding the continents and the islands, you're going to have terrigenous sediments really dominate. So pretty cool stuff.